This video is a summary of SN2 reaction. So first, SN2 reaction is a type of substitution reaction in which the mechanism is a concerted mechanism, meaning that the nucleophile attack and the loss of the leaving group step happen simultaneously. So here in this case, we have the nucleophile attack, and here is the loss of the leaving group. Both of these steps happen simultaneously. And a few things important that we need to remember regarding SN2 reaction as follows. First, there's no intermediate in SN2 reaction mechanism. And second, the reaction proceeds with the inversions of the configuration at the chiral center. So inversions of configuration. If the reactant carbon is a chiral center. And third, there is no racemic mixture being produced. And below are some of 4 of the factors that can affect SN2 reaction. First one, the structure of the substrate. We have seen already in previous lecture that the structure of the substrate can influence the SN2 reaction significantly, in which the less substituted the substrate, the faster rate of the reaction. So in this case, the structure of the substrate refers to the substitution of the alpha carbon. So substitution on the alpha carbon. And the relative rate of the different substrate are as follows. Methyl substrate have the fastest rate of reaction, followed by the primary substrate, followed by secondary substrate, followed by tertiary substrate. And in fact, tertiary substrate do not even go SN2 reaction at all. So no SN2 reaction. It is very slow to the point where it does not even happen at all. And one thing that we need to remember is that the less steric the substrate, then it is easier for the nucleophile to come to attack, and therefore the faster reaction rate. So less steric equal to easier to attack, and therefore faster reaction rate. So that is the effect of the substrate on the SN2 reaction. And the second factor that can affect SN2 reaction would then be the strength and the structure of the nucleophile. And the stronger the nucleophile, the faster the SN2 reaction would be. So stronger nucleophile equal to faster reactions rate. And below are examples of nucleophile that are considered to be strong, moderate, and weak. And in summary, we can then see that the more stable the nucleophile, then the weaker it is in the nucleophile attack, and therefore the slower the reaction rate would be. And strong nucleophile are basically substances that have large and negative charge on them and have low electronegativity on them. So for an example, iodine is rich in electron because it has a negative charge. And in this case, it is quite a large atom. So therefore, it is strong nucleophile. So all of these are rich in electron. This is why that we see all of them being negative. And the exception is over here, the amine, and this diol over here, and some of this. Although these are neutral, they are also classified as strong nucleophile. And the reason why is that the atom in them are big atom, and they have low electronegativity. So these are big and low electronegative atom. So that's why they form strong nucleophile. Strong nucleophile are substances that are willing to donate their electron in the nucleophilic attack. And for moderate nucleophile, this is where we see molecules that are rich in electron. However, the electrons are stabilized. So one example, the carboxylate. Even though that there is electron on the oxygen, the electron on the oxygen in this case are very well stabilized by resonance. So if we were to draw out the resonance structure, we would then see that this oxygen will be able to donate electron in and donate the electron to the other oxygen. So overall, the negative charge here is being distributed between these two oxygen, thus reducing the electron density on this nucleophile. And then another example would be the phenoxide. In this case, the electron here on this oxygen can also be donated to the ring to form resonance structure. And as a consequence, it reduced the electron density on this oxygen, therefore making this a moderate nucleophile. Even though it has a negative charge, the electron density are very well distributed in the molecule, making them stabilized anion and therefore moderate nucleophile. An example of the weak nucleophile are molecules, a reagent that are neutral or have high electronegativity to them. An example will be as follows. In this case, we have the fluoride, and the fluoride, even though it is negative, but because of its high electronegativity, it's less willing to donate the electron. Therefore, it does not attack very well. So although it is rich in electrons, it doesn't want to donate electron. Therefore, a weak nucleophile. And the other types of nucleophile are substances that are neutral. Because they're neutral, that means they're not rich in electron. So therefore, they are weak nucleophile. But because they have lone pair of electron, therefore, they are still nucleophilic, but weak nucleophile. So in the end, it basically is the amount of electrons and the stability of the electron that make a nucleophile a weak nucleophile or the strong nucleophile. All nucleophiles are basically rich in electron. And the less stable the electron on the nucleophile, the more reactive the nucleophile would be. So less stable nucleophile equal to more reactive. And some of the tools that we can use to determine how strong or how weak a nucleophile is will be first by using pKa. And second, aerial. So atom, resonance, inductive effect, and orbital. These are the two different types of tools that we can use to determine what is the stability of the electron on the nucleophile. And once we have used this to determine the stability of the nucleophile already, the less stable the electron on the nucleophile, the more reactive it would be. And third, the effect of the leaving group. So the more stable the leaving group, the faster the SN2 reaction rate would be. Because in the SN2 mechanism, the leaving group is breaking apart from the reactant carbon and taking the electron with it. Therefore, the faster that the leaving group can leave, the faster the SN2 reaction rate would be. And in order for the leaving group to leave easily, when it leaves with the electron, it has to be stable. Therefore, the more stable it is, the faster the SN2 reactions rate. So here are example of a few types of leaving group that we would consider to be great leaving group. So halide are basically good leaving group. And the reason why is that this atom right here are electronegative, meaning that the anion that they form are quite stable. So here in this case, we would then see that iodine is a better leaving group than bromide, and bromide is a better leaving group than the chloride. And another way for us to see this is that the conjugate acid of all of this have low pKa, meaning this anion right here are stable, and therefore they're good leaving group. And a few examples of all the types of leaving group that were also considered to be strong leaving group are sulfonates. Sulfonates are an example of sulfur-containing substances in which that once they break off, they actually become quite stabilized because of resonance structure. So here in this case, these types of leaving group here is called the tosylate group. And this is called a mesylate, and this is a triplet. Now, why are this good leaving group right here? The answer, if we were to be drawing out the resonance structure, we can see that this can form resonance structure really well. So the electron here on this oxygen can be donated to this oxygen and this oxygen as well. This is the same reason why the sulfuric acid is a strong acid, because the conjugate base that it forms is stable, just like this sulfonate ion that we see in here. And lastly, the solvent effect. The choice of the solvent can have a profound effect on the rate of an SN2 reaction. And from the previous lecture, we have seen already that the polar A product solvent favor SN2 reaction, because the polar A product solvent do not stabilize the nucleophile. So therefore, it's make the nucleophile more accessible to come in and attack the reactant carbon. So apolar A product solvent do not stable the nucleophile, therefore more available to react. So hopefully this is a quick summary to review SN2 reaction and the different factors that can affect the rate of an SN2 reaction.